Okay, very good. Let's start. So let me remind you what we are studying. Conics. Yes, I spend a lot of time printing it, so I want to make maximum use of it. So the classical definition is that conics are the intersection of a cone, which is the double cone, remember? So the mathematical cone is the double cone with a plane. And we think that when we do so, we have nice figure like the ellipse and cone and all that. And of course, you know that. But do you really know that? That's the question we're going to answer today, because being a mathematician in many ways is being unreasonable. And so you can say, yes, you show something that looks like an ellipse, but how do I know that it's actually an ellipse, right? Because our eyes could deceive us. There are plenty of function or curve that would look like an ellipse. Maybe there is like a very small power x to the 4 if I look at the intersection and so on. I don't know, right? You have to be skeptical at all time. And now what we really want to do is let's actually do this and show precisely that the intersection of a cone with a plane are made of the same object that we define in 2Ds, which were the loci, thank you guys, the loci of this condition here, this geometric condition, where we give ourselves a focus, a directrix D, and we ask the question of finding all the points, P in blue, that satisfy this distance condition. Okay, the third one that we also look today is to look at it from a purely algebraic point of view, which the classic Greek would hate, of course. Newton also hated that. Newton was somebody who thought that all the proofs should be geometric like the Greek. Of course, he introduced calculus, but he didn't like this algebraic approach from the French. But today, of course, it's a natural way for us to think. And it's interesting, of course, for us to look at all the connection between these different point of views. And then we look at how 3 is related to 2, somewhat. Okay, so here we have a little bit of work, because we actually have to do that. So I'm not going to do the fully general case where I've not lost anything in generality, really. But I'm going to take a code. So let me just do it in the Z. I'll just look at it now in the ZX plane. I'm going to take a particular plane. And the cone now looks like a pair of lines. Okay. And so I'm going to take a line here. And here is, I take it theta. And theta is the one I'm going to change. And Z is my cone. And if it's an angle here, then the cone is is described by x squared plus y squared equals z squared cotangent square of alpha. You can easily convince yourself that this here is r. This is r squared. And so when you take a cross section here, at least it's a circle. So we have the circle already, but we want to do much more, of course. If I fix this point here, so I can't have the circle, but it's easy to convince by just this argument, just writing this form of the cone, that the section of a cone with a plane that is perpendicular to the axis of the cone make either circle or a point. Now I want to parameterize this line. First the line, this is z equal in that plane. It's z equals tan theta, and I'm going to take, without loss of generality, I can always choose my point here to go to x equals 1. So it's tangent theta times x minus 1. Okay, that's a good start. But what I really want is the plane. right? And the plane that I have in mind is a plane that's, okay, I'm going to introduce the y-axis. It's a plane that is spanned by this vector and this one. Oh, actually, I'm going to take it here. And we know, that's what we've been working, if I give myself two vectors and one point, I can write the equation of a plane. So here is the line in the xz plane, and now I have to make a plane in the xyz space. And to do that, I introduce the basis E1, E2, and E3 perpendicular to the 2. And so I introduce the vector. It's a basis of the full space, which is made by E1, which is just cos theta 0 sine theta, right? Here this is just in the xz plane is cos theta sine theta, and I take it in the y equals 0, and so in the xyz in R3 it's cos theta 0 sine theta. I take E2 to be 0, 1, 0, and E3 to make a basis, I take it orthonormal. So I change the cos to a sine, and I change one sign. Sine theta 0 minus cos theta. I don't need E3 because I'm going to define my plane pi. So this is pi. Pi is spanned by E1, E2, and goes through the point 1, 0, 0. So that means xyz is in pi. So I can rewrite it as xyz equals the point P, 1, 0, 0, plus an arbitrary combination, linear combination of the vector E1 and E2. But that creates my new plane. So in this plane, I have coordinate, and this plane blue, in this blue plane, I'm going to use capital X, oh, no, capital, capital Y and capital X as my new coordinates. So I'm going to write X along E1. So this is my new axis X, capital X, and Y along E2. So it's X E1 plus Y E2. So remember, these are the equivalent of the lambda and mu that we had before, right? I just called them X and Y, and these are coordinates in this plane, XY. So if I spell that explicitly, what do I have? 1, 0, 0 plus cos theta. So it's 1 plus x cos theta. Then it's 1 times y. And then it's just x sine theta. So theta is a parameter. That's the angle of my plane. X and y's are coordinates in that plane. And so for any given x and y, I have a point in x, y, z that belongs in the plane. Now I want to take the intersection with, now I substitute these coordinates in, okay, so it's little x squared plus y square equals z square cos alpha. But to obtain, to obtain 1 plus x cos theta square plus y square equals x square sine square theta cos square alpha. So same game that we played yesterday, and we're going to play again a few times more today. We want to transform t's. Now, this is an equation for a set of points in the xy plane, and we want to transform that to one of the normal form of conics that we found by the second methods. And remember, the normal forms are written with the big X now, plus y square b square equals 1. That would be make ellipses, or x square over a square minus y square over b square equals 1. Of course, I can change x and y. It's just names. And that would make a hyperbola. Or y square equals 4ax. And that's the limit case of parabolas. So I want to change this equation to make it look like one of these, depending on the value of theta, right? And clearly, okay, do I have a plane? Here is a plane. So my point here is 1, 0, 0. I can't get the circle because I will have to do a translation, and that's not part of it. But I can make this intersection, and that would give me an ellipse. If I have this particular angle here, you can see this particular angle is the same as this one. So when the angle of the plane theta is the same as the angle of the cone, so when theta equals alpha, I expect to have a parabola. And then for larger angle, I would have one intersection here and another one with the other side of the cone. And that would be the hyperbolas. Okay. So it's in the note, it's given in general term, but the computation is not actually done. So I thought that I'll do it for particular case. You can argue it's not a particular case, that you can always rescale the value of z to choose that the alpha is pi over 4. But things are much easier if you take alpha equals pi over 4. You can do it in general. It's just the algebra is a little more difficult and boring. So in this case, we have 1 plus x cosine theta square plus y square equals x square sine square theta. So I put everything together. So I have x square times, I expand, cos square theta minus sine square theta. Then I have plus 1 plus 2x cos theta plus y square equals 0. Aha, so these are recognized. It's nice, cos 2 theta. And now I complete the square, right? Because I want to bring everything to a form of x plus something square plus y square equals 1. So let's complete the square. First, before we do that, okay, x squared cos 2 theta plus 1 plus 2x cos theta plus y squared equals 0. We can take care right away of the special case, theta equals pi over 4. in which case theta equals alpha. And in that case, the first term disappears, and we're left with y squared plus 1 plus 2x. Equals 0, and this is a parabola, of course. You can put it in the normal form by just doing a slight change of variable on x. So this would be in the xy plane. It would be a parabola going like this. Right. So when when y equals 0, x equals minus 1/2. And we go like that. Okay, so that's easy. Now we can take theta different than pi over 4. Which allows us to divide by cos 2 theta. Okay, so we write that, we put cos 2 theta in front. So that's x. Now I have to get this term here. So I need cos theta, but I have cos 2 theta outside, so I have to divide by cos 2 theta square. Now I've added this term when I completed the square, so I have to remove the extra 1. So that's cos square theta divided by cos 2 theta plus 1 plus y squared equals 0. But this guy here is cos 2 theta minus cos square theta, but cos 2 theta is cos square minus sine square. So I'm left with sine square. Minus sine square theta. Okay. So that's the term that is by itself, right, without x and y. So I divide everything by sine square theta to obtain cos 2 theta over sine square theta times x plus cos square plus y square equals 1. Oh, I square divided by sine square theta. And I'm done. Because now I can see that this is the same form as this guy up to a translation in x. I let you do that. You can see I can change x to x plus cos theta to cos 2 theta. That's just a translation to put the axis in the middle of the ellipse. So it has exactly this form of this form, depending on the respective sign of the coefficient in front of x and y. Right? It doesn't matter which one it's. Here the two signs in front of the square are positive, and here the product of the two signs is negative. Okay? So we have two cases. So we have 2a, which is theta. If we take theta less than pi over 4, then we have cos 2 theta is positive. And so these two terms as positive. And so we have something of the form x tilde over a square plus y tilde square over b square equals 1. With x tilde equals x plus cos 2 theta, or cos theta over cos 2 theta, and y tilde equals 1, of course. Or theta bigger than pi over 4. So that's for small angle, right? So as small angle, I get the ellipse. if I increase the angle, 2 pi over 4, I get the parabola, and then even more, I get cos 2 theta negative, and then I have x tilde over a square minus y tilde square over b square equals 1, with x tilde equals y, and y tilde equals x plus cos theta over cos 2 theta. So in this case, I get ellipses. And in the other case, I get hyperbolas. So is the proof, yeah, go ahead.
1 minus cosine square theta over cosine 2 theta. Is it sine, negative sine square theta over cosine 2 theta?
Which, oh, sorry, where?
First word on the right hand side. On the bottom of that. Yeah.
Here?
No, the bottom of the first one.
Here? Why is that? So I have cos 2 theta minus cos square 2 theta, cos square theta over cos 2 theta, right? Oh, you're right. Let's see, let's do it. Let's do it. So this is cos square minus sine square. Minus sine square. Oh, so I have a cos 2 theta that still need to. Okay, so it's okay. So this is actually sine square over cos 2 theta. Was that your objection? Okay, and so I have a cos square. Oh, okay. Thank you. I have cos 2 theta over sine square theta times y square equals 1. And I have cos square 2 theta. Okay. So now, yes. Now this is right, and I just have to do this again. Cos 2 theta. Okay, let's see. Let's take one step up. Do we agree now? Okay. Yeah, I forgot this. Thank you. And I think it's right, yeah. So this term is always positive, and this is the one that changed sign. So that's the one that gives you the 2 case. Very good. Thank you. Okay. So now you can say, okay, we've done one plane. Is it true for any plane? Well, after that, it's a little bit of computation. The one case that doesn't fit, of course, is the case where we take a plane that's perpendicular, that contains the axis, in which case we have 2 lines. Right? It's a trivial computation. But all the other one can be mapped to that one, up to a translation, and translation in x, y, z. You can map all the cases. So that finished that part, that the sections are, the section of a cone are really the conics, defined by 2. But now we want to go to part 3.1, which are the quadratic equation. So I start with the most general form, ax plus by square, bxy plus cy square plus dx plus ey plus f equal 0. And I want to know all the solution of that equation. And my claim is the solution of this equation are the conics, but also, so in addition, we have the null set, so that's easy to see. You take, for instance, x squared equals x squared plus 1 equals 0, right? You choose the coefficient, and you see that there is no xy in R. So we're looking for xy in R. Single line. And that's given by x minus y square equal 0, for instance, or parallel line. We'll see. None of these can be obtained as a section of a conic. Okay, so let's see how we're going to do this. First observation is that if b equals 0, we can complete the square. We can complete the square and map that to one of the forms that we had before. So that case is easy. And you obtain all the normal forms. So what do we do in general when b is not 0? Well, what we've done when we complete the square, we do a translation. The other operation that we can do is choose the axis of our coordinate system to align it with the axis of the conics. So if we have an ellipse, the fact that the b is different from 0 is just that the fact that you rewrite it in a way that the ellipse is not aligned with the main axis. So if we rotate the axis and choose them properly, the b is going to disappear in that new set of coordinates. So b different from 0, the idea is to rotate the axis. So if we have, let's draw an ellipse along the So if we have an ellipse like that, and this is very important because it's exactly what we're going to do in greater generality starting next week when we'll talk about isometries and orthogonal matrices. Okay, this is the worst ellipse I ever drawn. So this is little x, little y, and we want to rotate it to x and y. So we want to rotate the axis so that expressed in this new axis, the ellipse is along the main axis. And I know that as soon as the axis of the ellipse coincides with the axis of the coordinates, I'm in a normal form, right? I'll be back in this case. So this rotation, the geometric effect of the rotation is going to change variable to big X and big Y, where in this new variable, B should disappear. So what is this rotation? Well, the new axes are little x cos theta plus y sine theta, if you look at the image, and y equals minus x sine theta plus y cos theta. You can also, this is what we're going to do starting next week when we look at orthogonal matrices. Think of it as a matrix R applied to x and y. where the matrix R is cos theta, sine theta, minus sine theta, cos theta. And this is an example of an orthogonal matrix. So we'll do a little bit of algebra. So for, let's call C cos theta and S sine theta, just to make it faster. Now, there is something very nice that we'll see about orthogonal matrices, is that the inverse of an orthogonal matrix is the transpose of the matrix. So this is the best possible world where you don't have to do any computation to actually compute an inverse. And indeed, if I inverse these by whatever method, I can write it as x times c. All right, let me write this explicitly. Minus y sine theta, and y equals x sine theta plus y cos theta. And you see that it's right, it's x and y equals a matrix R transpose times xy. Right, if I transpose R, I've got the sine theta and minus sine theta change. That's all. So for next week, starting next week, please notice that these matrices have the nice property that R times R transpose is the identity, which implies that the determinant is not 0, so we can invert them, and that the R transpose is R minus 1. So it's a preview. Okay. Now, I want to do that rotation, but I'm not going to do the general case. I'm going to assume that we've already done a translation that get rid of x and y in the particular case where we don't have parabola. And I'm going to do a particular case, again, which is called the reduced form, where we've already done a translation, where we obtain ax squared plus bxy plus cy squared equals 1. And I'm going to assume that a is bigger than c log without loss of generality. If it's not the case, I can always change the name x and y for it to be true, a big C. Okay, so now I'm going to substitute this in here. So what do I have? I have a times cx minus sy squared plus b cx minus sy times sx plus cy bxy plus c times sx plus cy squared, little c, equals 1. So remember, what we're trying to do is to choose the angle theta to get rid of the b. So to get rid in the new coordinates of the coefficient in front of xy. So the coefficient of xy are going to have contribution from all the terms for the coefficient of xy. So from the first one, I have minus 2cs times a. The second one, I have c square x minus s square minus x square b. So I have plus b times c square minus s square plus 2c s times c. equals 0. So again, I recognize here this is cosine 2 theta, and this guy here is 1/2 sine 2 theta. Okay, so I can rewrite c minus a times sine 2 theta plus b cos 2 theta equal 0. So again, it's equal to 0 because in the new coordinate, capital X and capital Y, I want this term to disappear. The whole point is to choose which angle so that in the coordinate I do not have the cross term. Well, so there's a simple case. If A equals C, this first term disappears. I can choose theta equals pi over 4. So that's the first case. So let's assume that A is different than C now. And in that case, I have tangent of 2 theta equals B divided by A minus C. Okay, so what is the trigonometry of that? So this is a little triangle with side A minus C and B, and angle here to, oh, did I hear remote? Ah, thank you. You have to be more forceful. 2. Okay, thank you. So this is the angle 2 theta. This is the hypotenuse h. And h is the square root of b squared plus a minus c squared, Pythagoras. Okay, so I'm going to need all that. So I choose this angle, and now I can do that. And now I can rewrite, I can go back here, star, and simplify that whole thing. So choose theta such that tangent 2 theta equals b over a minus c. And then I use a minus c, b, and h to rewrite all the cosine and sine in terms of the coefficient. So that's a little bit of trick. But when you do that, what you obtain is a plus c plus h over 2 times x squared plus a plus c minus h over 2 times y squared equals 1. Okay, so you can see that this is 1 over a squared, and this is, well, depending on the sign, it's going to be plus or minus 1 over, so it's either 1 over b squared or minus 1 over b squared. This term is positive, so this one has the change of sign, depending on whether we have ellipse or parabola. So I have, depending on the sign, so if I call this alpha and this beta, so I have alpha times beta is positive if the product of the two is positive. A plus c plus h times a plus c minus h is positive. And now I can use the definition of h to write this condition purely in terms of a, b, and c. And that condition is b squared less than 4ac. So that's very nice. Now we can define delta equals b squared minus 4ac. Now it looks like the quadratic formula. It's all chosen for that, of course. And we have the different case. So we have the different cases now to discuss. We have b squared minus 4ac okay. Okay, let me do that explicitly because I think I have a sign somewhere missing. I don't know if I don't know if this sign is correct. So let me do it explicitly. A plus c plus h. So I have this is like a plus b times a minus b. So I can rewrite that as a plus c square minus h square positive. But h square is b square plus a minus c square. Okay, so this is a square plus 2ac minus plus c square minus b square minus a square minus c square plus 2ac. It must be positive, so all t's disappear. So I have 4ac minus b square positive. So I have 4ac bigger than b square, or b square minus 4ac negative. Good. So that's the case where the product of the two coefficients is positive. So delta negative, and in which case I have either ellipsis or the empty set. Right. So that's case 1. Case 2, I have b squared minus 4ac equals 0. So in this case, I have either something of the form alpha x squared equals 1 or beta y squared equals 1. And so that gives me two lines, which is x equal plus or minus 1 over alpha, or y equals plus or minus 1 over beta. Now, if b squared minus 4ac is positive, then I have a hyperbola. Oh, ellipsis. Okay. Very good. Now, something that, so you see that, again, rotation translation, we can start with the full form and get all the case of the conics with a little bit more elbow to make sure we have all the case. We've made some assumption in the meantime here. I want to make two comments. First, if you look at T's, it has a very nice structure. So if I take axy plus bxy plus cy squared, I can rewrite that in terms of matrix as xy times the matrix A, B over 2, B over 2, C. times xy. And if I call that m, then you see that the determinant of m equals ac minus b squared over 4. And it's therefore the determinant of m that decide in which case we are. So it's something very interesting with this quadratic form is that you can use matrices also to formalize them. And the matrix that you obtain, the determinant of which is meaningful in terms of the type of geometric set that you obtain. Okay. Whereas typically you think about matrices only related to a plane and lines, so linear element. You see quadratic form can also be encoded by matrices. So more generally, that's theorem 57. It essentially has the whole flavor of what we've done. It's just one of these annoying where you have to classify and make sure that you get everything. So in terms of algebra, it's the same, but a little bit more general, carrying a lot of parameter and coefficients. But morally, it's completely equivalent. That if I take ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, and I compute delta equals b squared minus 4ac, then in full generality I have the following case. I have delta negative, which is what we look at, in which case I have ellipses, a single point, or the empty set. The single point is the apex of the cone, of course. If delta equals 0, we have parabolas, two parallel lines, one line, or the empty set. And if delta is bigger than 0, then we have hyperbolas and two lines that cross, non-parallel line. And that's the general classification of the quadratic function, quadratic in two variables. Of course, you can extract other conditions to say in which case, subcase you are and all that. You can branch, but the important is the big picture, is that this quadratic function contains all the conics plus the two parallel line and the line and the empty set. Right? That you wouldn't be able to construct geometrically. Okay, so that's just to give you a flavor of conics. Historically, already in classic Greece, they had volumes and volumes of properties, of interesting properties of conics. And that carried out later on in the 17th century and 18th century. People were completely fascinated by multiple properties of the conics. Show you some nice with reflection, but you can ask multiple questions about the set of tangent, about the set of the curvature of conics at different points, what the property of the best fitting circle, and so on. And so it's a whole universe of property of conics, mostly neglected. In a way, it's not part of mainstream mathematics. Sometimes it gets useful in some area of physics when you look at orbits and things like that. But more important, the topic itself gave birth to multiple areas of modern mathematics, like function of complex variable, geometry of surfaces, and so on. And it has also very nice connection, as you already see, to the next chapter, which will be on isometry, orthonormal basis, and orthogonal matrices, which is really the full basis, the building block of most of linear algebra, as you've already seen. Thank you.